All right, we have our last presentation of the day. Amin is going to present his work. He's working in the area of smart grids, energy market, electricity energy market, and he's also working with Dr. Hashim. With that, Amin.
Thank you, Robert. Hello, everyone. My name is Amin. I'm bishop to the business department and under supervision of Dr. Hashemi. And for today, I would like to talk about a recent research, which is an uncertainty-centric framework in electricity markets using multi-agent reinforcement learning. So most of you may have heard about the Biden Energy Plan or the United States Energy Plan. So in August 2022, the Congress passed and President Biden signed into law the IRA, and the IRA is the largest investment in clean energy in the U.S. system. So there are two main goals in this plan: to have the clean electricity by 2035, and to have the net zero carbon emission energy by 2050. So the power sector is the second largest source of the climate pollution in the U.S., around 25%. So the clean electricity and moving for the clean electrification is the cornerstone of decarbonizing the economy to meet these two goals. So the clean energy means the cleaner air, better homes, and more jobs. Good news. So let's see how is the trend right now. The current, this is the research from the EIA, and the current research shows that the current clean power capacity are enough for powering the 64 million American homes. That's pretty good, but that's not enough. So most of the study shows that and suggests that the more renewable investment and more renewable generation is needed to meet the country's goal. And from the research shows that most of the growth in renewable generation from the solar and wind. So another study we consider these two kind of the renewable generation. Let's see what are the challenges. Historically, the main problem with the renewable generation was the initial cost, but it's not a big deal today because right now the cost of generating the electricity with the renewable generation, wind and solar, is less than the cost of generating electricity by the other sources, even the natural gas. So that's a good news. But what's the problem right now? The main problem with the integration of the renewable generation in the power system is the uncertainty. So the renewable generation highly dependent on the climate change, the weather. So we are living in Kansas, we are familiar with this and big change. So the weather is changing a lot. So the output of the renewable generation is changing a lot. So this is a big deal for integrating more and more renewable generation in the power system and in the electricity market. Let's see how the electricity market works. So same as the other products, the electricity market has the seller and the buyer. So the sellers are the generators, the buyers are the end user and customers. We have some other players in between that we call them reseller or retailer or a distributor. So these resellers purchase the power in the wholesale market from the generators and resell and distribute the electricity among the end users. So we have two different markets. In the wholesale market, there is a bidding problem. So this is a bidding problem. This procedure, this game, the bidding game is between the generators and the resellers or the retailers. The big constraint here is the power balance. So what means? That means any power that is generated somewhere in this market should be consumed somewhere else. There is no option of storing the electricity in this market, at least right now. Hopefully in the future with the huge electric pack, we will have this option, but right now we do not have the option of storing the electricity in this market. So there is And ISO that we call the independent service operator in this market who controls this market. For example, the United States has 9 different ISO. For example, for the electricity market in the Texas, there is an ERCOT, we have ISO for the California, for Kansas, there is SPP. So this ISO solved the economic dispatch and the unit commitments for during the different time frames. And this unit commitment and economic dispatch is something like the resource allocation. And there are, so as I said, the optimization of the power system is a real time. Okay, so power is generated somewhere, should be consumed somewhere else. So these two problems should be solved in different time frames: the long term, short term, the day ahead, and in the real time. The real time, for example, in the United States, between 5 minutes to 15 minutes. So suppose that we are injecting more and more renewable generation in this market, why, such as the wind farm and solar farm. So it means we are injecting more uncertainty in this market. So solving the problem of economic dispatch and unit commitment is getting more and more complex. On the other side, we have the retail market, which is the game between the end users and the retailers. And the most important product in that market is the demand response, which is the retailers use that demand response to incentivize the end user to participate in the program to help the grid during the peak demand hours. And the main demand response method is the dynamic pricing, or changing the electricity price in the retail market. Time of use is the most important and the popular method right now. But we use a dynamic pricing, which is a modern method. And so generating more renewable energy, like the people use of panels in this market, is changing this market as well. And so more uncertainty in this market. This is our model that we use. So we thought there are a lot of work that consider the wholesale market, and there are a lot of previous work that consider the retail market, but we consider both markets at the same time in our research. So we specifically investigated the market in day ahead and the real time, because these two markets are really dynamic. And so our ISO defined the clearing price for the beats. And so as you see, the wind generation is the highest priority in sorting the beats. Excuse me. The wind generation is the highest priority because it's the cheapest. So basically, we are facing with a 2-level optimization problem. So we have one level in the wholesale market, and there is another optimization problem in the retail market. So these 2-level optimization problems should be solved and online during the time, in all time frames, the real time, day ahead, and during the long term. So our solution to solve these two-level optimization is to use the reinforcement learning. So we locate one reinforcement learning agent in LSE location and one reinforcement learning agent in the prosumer agent. So the LSE agent tries to manage the electricity distribution over the retail market, and then the prosumer agent tries to manage the prosumers. And the prosumers are those consumers that they have ability of selling back the electricity to the grid. Let's talk a bit about the background of the RL. So RL is a kind of is a category of the machine learning techniques. So we have the supervised, unsupervised, and the reinforcement learning. So in reinforcement learning, we have the agent that is interacting in an environment. So the agent select an action environment and receive a reward. During the long run, the agent can learn how to react in that environment to maximize the accumulated reward. So we use the DDPG, which is a model-free reinforcement learning, and it's a combination of concept optimization and pure learning. The DDPG has an action-critic structure. So it means there is an action network which select the action, and there is a critic, which criticizes the actions selected by the actor. And there is a replay buffer, and basically each of those actor and critic has two networks. So if you want to train a DVPG agent, you have to train 4 different networks. This is the system model that we have. This is the contribution that we have. So as I said, in reinforcement learning, the agent is interacting an environment. So the environment is the retail market, the electricity market, the retail market, and the wholesale market. So we have the LSA, which is the blue one, is located in the LSA location, is connected to the environment, and manage the retail electricity market, the distribution of the electricity in the retail market. At the same time, the LSA should participate in the day-ahead market and the real-time market in the wholesale. And we have the PA agent who manage the prosumers and is connected to the environment, and we connect time series forecasting as well. So the time series forecasting is to come back and to capture the wind uncertainty coming from the renewable generation from the power plants. So if you remember, we had 2 different sources of uncertainty, one from the generation side, one from the PV rooftop panels from the household side. So this LSA can help the LSA to capture the wind uncertainty from the wind generation, and the multi-agent reinforcement learning algorithm is for capturing the dynamics of the retail market and combating the uncertainty coming from the PV rooftop panels. So, as I said, the time series forecasting forecasts the wind availability for the next 24 hours because the LSA should participate in the day-ahead market. So we need the information from the next 24 hours. And how to mitigate the uncertainty inject from the wind farms. And on the other hand, so the multi-agent reinforcement learning mitigate the uncertainty inject from the PV rooftop panel, as I said. And we have the PA who controls the energy management of the prosumers. This is the simulation setup. So we use this is the IEEE 5-bus test system. So this is a standard system. So to evaluate our framework, we tested our framework on the IEEE 5-bus standard system. So here you see we have 5 different buses. There are G1 and G2. G1 and G2 are the 2 conventional generation. So we have the wind farm connected to bus A, which is one source of uncertainty. We have the prosumer network, and also prosumers are those consumers, those end users with the PV rooftop panels. So another source of uncertainty in bus A or bus B, and we have the other rows in bus B and C. So the LSC controls and manage the energy, the electricity distribution over the bus B, and C. At the same time, the LSC should participate in the wholesale market, producing power from the power plants. So the first result shows that this is for the time series forecasting. And this result shows that the LSC is able to predict the wind generation over a window of the 24 hours. So that's good, and we can count on this result because we need this information for the LSA. So basically, the LSA need this information to participate in the day-ahead market and the real-time market. So to compare our method, we define a baseline method that we call uncertainty range. It means suppose that there is no option for forecasting. So one scenario is to have the forecasting engine to forecast the wind generation for the next 24 hours. And the other one is suppose that the current day, the next day waveform of the wind generation is same as the current day within a range. And we consider a 10% range, the uncertainty range for this scenario. So our simulation shows that our model is able to dynamically change the price. So the plot in the middle is the electricity price. The plot at the bottom is the battery from one prosumer. So the blue curve is for our model, and the dotted one is for the uncertainty range scenario. And this shows that our model is able to dynamically change the price during the day. And the other one is the battery span. So our model shows that, so our model is able to use the whole span of the battery, and this is a good result that we have. The other one is we compared our model with the current pricing waveform, pricing framework. For example, we compare a model with the time of use of two samples, one from the Evergy, which is a retailer located in Kansas, and we compare with the Edison, which is a retailer located in the California. So our model shows that for dynamic pricing framework can lead to a better profit and a smaller peak to average. And the peak to average basically in power system is defined for the total, the network total demand. And that's an important matrix in the power system. So another observation that we have is we found that our agent, so this is for combating the uncertainty coming from the household side. So the result shows that during the, our consumer agent decided to charge the battery at the beginning of cloudy days. So if you look at on this black curve, so this is the battery level of one consumer. So it shows that during the cloudy days, so the agent tried to charge the battery at the beginning of the day. But during the sunny day, the agent just wait for the excess power, because in the sunny day, we will have excess power from the PV rooftop panels during the sun peak hours. So it's good to wait for the excess power, charge the battery to support the grid during the afternoon, because basically in power system, we have the peak demand during the afternoon. So we need the battery to be fully charged to help the grid during the afternoon. So to summary our recent research, so I joined that we studied the impact of the renewable energy resources on uncertainty on both wholesale and retail market. And we formulated the problem with a two-level optimization problem. And we showed that this two-level optimization problem can be solved in real time with the multi-agent reinforcement learning using the time series forecasting. The time series forecasting is using to combat the uncertainty coming from the wind farm, coming from the generation part. And the multi-agent reinforcement learning is using for distributing the electricity among the retail market and combating the uncertainty from the PV rooftop panels. I just want to let you know that about our future research and current research. So, as you know, the number of the EVs, the electric vehicles, is increasing as well. So this is a projection until 2030. And the study shows that most of the new cars in the future, in the next decade, will be the electric vehicles. So this means increasing the demand and increasing the uncertainty, new source of uncertainty. Why? Because we don't know the behavior of the EV owners, where they want to charge the battery, when they want to charge the batteries. So this is a new source of uncertainty. And this is a study that is done in 2018, and it shows that this is a study for the Texas and California. It showed that with the current infrastructure of the power system in these two states, so if all the cars are EV, so they definitely go beyond the capacity of the power system. So this means power outage or the network blackout. This is not good. So for this one, we would like to use the cooperative multi-agent reinforcement learning, which is pretty new. And so this is our current research that we are working right now. Thank you.
Thank you. Do you have any questions?
So you have implemented DBPG algorithm for detection, right?
Yes.
So if you try any other algorithm like optimal polygon
So before this DBPG, we use the DQN. So the basic difference between the DQN and DBPG is the DQN is used for the discrete action state, but the DBPG is for continuous action state. So the DBPG works together. So we can work with continuous action state, and so from one is continuous action. So, but this is a plan for using the DPO, especially for the operative one, but we do not use the DPO.
So what is better in terms of performance or program you either export it?
So between the DQ and the DPO, yes, the performance of the DPO is better. So we can handle as I said, the DPO can handle continuous action state. So our action of both agents are continuous. So the LSD, let me show you. So this one, the LSA action is determining the price in the retailer. So we are doing the dynamic price. So within the range, the price can change. So it's a continuous. DQ cannot handle this. Okay. So the PA agent is trying to determine the battery current, charge, discharge in the range, the different rates. Okay. So this is continuous average. The DQ cannot handle this. PPO can handle, but the difference between PPO and DPG, so one is offline, the other one is online. The PPO and DPG both are pretty new.
So dynamic pricing sounds wonderful as a problem to solve. But it's also a disaster in the sense of when did we have the deep freeze in early February of
Texas.
22 or 21, I forget.
21.
Where people in Lawrence, householders in Lawrence are, for the next 5 years, will be paying for the disaster of gas pricing in that freeze. And just to put it on a personal basis, how would you like it if KU decided to use dynamic pricing? You will not know what the cost of attending a lecture is tomorrow until midnight tonight.
So the dynamic pricing, so we have a cap in the dynamic pricing aspect.
Well, obviously we don't. Well, look at the gas prices during the
Yes.
freeze and look at Texas during the freeze. We don't have caps. Look at Enron in California 1 or 2 decades ago.
Yeah, what happened in Texas was an emergency situation. So that happens because the network blackout. Okay, so we are suggesting that we can manage. So in the future, there are more and more households that they have the PV rooftop panels. So we are suggesting a framework that we can handle those sources of the new electricity in the future. Suppose that most of the households in the same time, 2021 Texas, some households, they have the PV rooftop panel. So if they know something is happened, for example, tomorrow, so they can charge the batteries and help the grid during the emergency time. So yes, the dynamic pricing normally, same as the time and fuels, has a cap aspect. But during the emergency time, yeah, I agree with you. There's no cap. But the whole idea here is to manage the new source of the electricity.
Are there any other questions?
I guess maybe it's a bit more kind of a market design in the sense that we have a supply and a demand, right? So we have a limited amount of supply, and kind of the demand is also changing, right? So really, how we can kind of balance between these in terms of like, so basically, your dynamic pricing is trying to do that.
Yes, suppose that if the LSA see the demand is increasing, so they can increase the price, and then this incentivizes the household to use their local, for example, PV panels instead of purchasing power from grid or during the off-peak demand hours. So they can. So we have two different prices in the retail market. So since we have the consumers, we have the sell price, we have the buy price. So once that you have the PV rooftop panels and you're able to sell back the electricity to the grid, so there is a sell price as well. So these two prices can be different. Right now, in the United States, these two prices are exactly same. Okay, with the smart meters. But with this framework, we can differentiate between the sell price and buy price. During the peak demand hours, the sell price can increase and incentivize the households to the sell price can decrease and incentivize the household to purchase the power from grid, then purchase power from grid to charge the battery. So from the grid perspective, it's good. The batteries in the household will be fully charged to help the grid during the emergency time.
Any other questions? If not, thank you.
Thank you.